Hi, I'm Ian Bosch. For my ENCMP 100 contest entry, I made a 16-bit simulated computer in Python. As you can see, it's currently running Snake, and on the side there is the source code of Snake, written in the computer's own assembly language. So, how did I get to this point? Well, the project grew organically, kind of like a tree. This project has its roots in standard Python and NumPy. Using these, I built the three core components of this project: the CPU, the memory, and the ports. Each of these is a separate class in its own file, as I figured that would be better for organization. Next, I made my first port, the console port. All it did was output ASCII characters to the console. Finally, I was ready to make my first program. However, at this stage, this required manually entering hexadecimal numbers to program the computer. So the very next thing I did was make the compiler. The compiler is like the leaves of the tree. It performs photosynthesis to help the tree grow. The upgraded version of the first program is much easier to read and much more versatile. Next, I added a virtual disk port that let me load files from my computer. This allowed me to make a simple bootloader. To make the disk port, I had Gemini help with the utility logic that was outside the course scope. This included using the OS and fnmatch modules to search for files and sandbox the computer to minimize cybersecurity risks. I also implemented rudimentary memory faults. By this, I mean that the virtual computer could run in two modes: kernel mode, which can access all of memory and all the ports, and user mode, which can only access some of memory and only some of the ports. If the computer was in user mode and tried to access restricted memory or ports, then it triggered a memory fault and shut down. The next major milestone was a complete refactoring of the compiler and the port system. To upgrade the compiler, I had Gemini help me build these helper methods. They use the regex module for string parsing, replacing the clunky manual parsing that I was using previously. I also used the resolve expression method here to limit eval to just basic math. This makes my compiler powerful while remaining safe. I also had to refactor the ports because I had hit a wall in development. See, the disk port looked like this. It was large, clunky, and difficult to maintain and use. So I switched to a simpler architecture with just three sections: a command and status register, a data register for bulk transfers, and a 16-bit shared scratchpad. Now, instead of needing to keep track of which memory location triggered what, I could just write the arguments to the scratchpad and send a command to the port. In fact, this setup worked so well that I adopted it as a universal standard. I created a port interface that acts like a USB adapter. It plugs every piece of hardware into the same connector. Now, I can build a new port just by filling in a few specific methods. I applied a similar strategy to the screen. I had Gemini help me write the screen.py file, which handles all the Pygame interaction. Because Pygame is completely contained in screen.py, I could swap it out for matplotlib or something else, and the only thing I would have to change is the screen.py file. The second last milestone was implementing an interrupt system. To understand interrupts, think of a doorbell. Say you're reading a book and the doorbell rings. You don't just lose your place, you put a bookmark in, then you answer the door, and then you go back later. And that's exactly what the CPU does. When it receives an interrupt, it saves its spot, it goes to deal with the interrupt, and then it comes back later. So as you can see from this diagram, interrupts can come from three places: from inside the CPU, from memory, and from the ports. This diagram shows the different levels of priority. Although the middle three rings all have the same privileges, the center ones have priority for interrupts. Finally, there's the most challenging part: saving your spot with a bookmark so that you can go back later. I did this by using three different sections of memory to store data about where to return to. The last major milestone was using Pygame to implement a screen and collect user input in real time. Finally, let's look at how the Happy Birthday program changed over the course of this project. Version 1 and 2 were simple because I was just using the console, but for version 3 I had to make my own font, a string printing routine, and a bunch of graphics utilities. One major challenge that I faced was when I found a bug in my assembly program. I didn't know if there was a problem in the assembly or in the computer. It was kind of like trying to write a book in a language that you're still making. Over the course of this project, I learned a lot about Python, computer architecture, and programming. I will be continuing this project in future so that I can keep learning. I would like to thank Texas Instruments and Zilog for inspiring me with the TI-84 Plus CE. I would also like to thank the ENCMP 100 instructors for running this contest and inspiring me to challenge myself. Finally, I would like to thank God for giving me the talents that I used to make this. Thanks for watching. I hope that you learned something.